to today's webinar, How to Reduce Costs Through Energy Demand Management. Before we begin, I want to go over a few housekeeping items. First, today's webinar will be recorded and is going to be sent to attendees about 24 hours after the webinar is finished today. Second, there will be a couple of opportunities to ask questions during the webinar. Please type them into the question box in your webinar dashboard. We'll try to address them at the midway point and at the end of the session today. So again, thank you all for attending, and I will pass the session on to Jared with Power Solutions to get us started and introduce today's speakers. Go ahead, Jared.
Thank you, Shannon. Again, this is Jared Burke with Power Solutions. Thank you, everybody, for attending. As Shannon said, today we're going to be speaking about reducing demand costs through melt system optimization and demand control software. I'm joined today by Mike Nutt with Inductotherm and Dick Winsimius, former plant engineering manager for Canon Muskegon. Real quickly about the Power Solutions and Inductotherm partnership. Our companies have teamed up to enable metal casters like yourselves to drastically reduce electricity costs while maintaining your high levels of production standards. Inductotherm furnaces easily integrate with Power Solutions' Spara DM industrial energy management system and can even be shipped pre-wired for integration with Spara, so facilities can optimize peak demand levels and participate in smart grid programs. Now with that, I'd like to kick this off and introduce Mike Nutt, who has been with Inductotherm for over 26 years. He's currently the Senior Sales Manager and Director of International Sales. Prior to this, he spent 14 years as the District Manager for the territories of Ohio, Michigan, and Wheeling, West Virginia. And before that, he spent 11 years as a Field Service Engineer. So with that, Mike, why don't you take it away?
All right, I appreciate that, and appreciate the opportunity to participate in the webinar. So I guess if we want to move to my first slide, right now I'm seeing I'm not seeing my first slide.
Sorry about that, Mike.
No problem. Okay, so anyway, if you could back up one more. Okay, yeah, anyway, so the purpose of this presentation is to discuss the importance of maximizing the melt system production at the lowest kilowatt or kVA of demand as part of your overall energy management program. In the presentation, I'll review the importance of melt shop power supply utilization, efficiency, performance, and how it will impact your required power demand. I'll cover how this will influence the connected kilowatts or kVA demand for a given production rate, and then finally show how by increasing melt shop utilization, it will increase the poured tons per kilowatt or per kilowatt of demand. Next slide. You can go on to the next slide. Okay. So if we look at a typical melt shop energy usage, you'll find that melting represents the highest percentage of energy consumption in a typical foundry. Therefore, offers the best opportunity for energy demand and energy usage cost reduction. In this pie chart, you can see that the melting represents over 50% of the overall melt shop energy usage. Next slide. Looking at the key factors that influence production versus demand, these include efficiency, melt shop performance, the power supply technology, and the power supply utilization. These factors are The factors that are specifically part of power supply utilization include equipment configuration and the type, the operational practices, melt preparation, the charging process that's involved, and also how the furnaces are poured. Next slide. If we're looking at the efficiency first, over the years there's been substantial gains in induction power supply efficiency. Today's technology, which is solid state power supplies, are achieving efficiencies in the areas of 98%, which is substantially higher than earlier technologies of solid state or early solid state and or hard state technology, as shown in the slide. It's recommended that Foundry should review the efficiency of their existing melt system to see if substantial gains can be achieved by newer technologies. Next slide. When we talk about efficiency, you need to look at batch melting versus heel melting. As shown in the illustration, batch melting is typically about 7% more efficient than heel melting. This is a result of higher coil efficiency during the early stages of a batch melt cycle. As an example, looking at iron melting, 7% can equate to as much as 30 kilowatt hours for every ton melted. 30 kilowatt hours over a year's production can add up to a substantial amount of added energy usage and energy cost. Next slide. Another factor mentioned was melt system performance. In order to maximize the achievable production for paid demand, it's important that the melt system have the ability to pull full power throughout the entire melt cycle. Today's true batch melting systems should be designed to pull full power from the very beginning of the melt cycle with an initial charge throughout the end of the melt cycle until the target temperature is reached. Some technologies or older technologies may not be capable of reaching full power during the early stages of the melt, and as a result, you're not taking advantage of the total demand that you are paying for. Next slide. Another part of performance associated with power supply technology is kilowatt output versus line kVA and line power factor. All power supply technologies do not lend themselves equally to demand control. As shown in these charts, one technology maintains a consistent high power factor at all power levels, whereas some technologies operate at a lower line power factor at reduced power levels. This also means that at reduced power levels, your input kVA will be higher as compared to those running at a consistent high power factor. As a result, these systems may not get the full benefit of demand control due to the high line kVA or power factor penalties at reduced power levels. Next slide. Another factor discussed is power supply utilization. Power supply utilization is a ratio of melt time to the overall total melt cycle time. the total melt cycle time is made up of the melt time as well as time required for tasks such as temperature measurements, lag removal, chemistry analysis, pouring, and initial charging of the furnace. We sometimes refer to this as the off time or hold time portion of the melt cycle. In this specific example, the melt time is 40 minutes. The time required for off time functions is 22. Utilization is 65%. Next slide. If we look at another example where the melt time is longer, let's say 60 minutes, however the off time is only 14 minutes, therefore the result is your overall melt cycle time is 74 minutes and the power supply utilization is now a little higher at 81%. This example illustrates how being more efficient with the off-time functions can increase the utilization of your melt system power supply. Next slide. In the next slides, I'm going to compare the hourly pour rate versus the required power demand for 5 different melt systems, 5 different melt system operations, all producing between 6 and 7 tons per hour, all with varying power demands. This will illustrate that by maximizing efficiency, melt system configuration, melt system performance, and utilization, the highest production per kilowatt or per kVA demand can be achieved. Next slide. So the first example, which we'll call Foundry number 1, is an illustration of a basic one-on-one mains frequency heel melting operation with a demand of 5,000 kilowatts and a melt rate of 10 tons per hour. Assuming a power utilization of 65%, the pour rate would be 6.5 tons per hour. The power density is very typical for mains frequency of 250 kilowatts per ton. Next slide. In the Foundry number 2 example, also being a mains frequency heel melting system, operating at 450 kilowatts of demand. However, in this case, with the second furnace and with a butterflying operation, allows them to increase the power supply utilization to 75% and achieve a pour rate of 6.75 tons per hour. Although they're operating at 500 kilowatts of demand less than the previous example, because they increased their power supply utilization to 75%, they're able to increase their production at a lower kilowatt of demand. Next slide. Foundry number 3 is a medium frequency heel melting operation. When we look at this system, we need to take into account that today's medium frequency solid state heel melting systems offer increased efficiency and a higher melt rate versus line frequency systems shown in the examples of Foundry 1 and 2. Medium frequency also allows us to utilize smaller furnace capacities, which reduces holding energy and puts more energy into the melt. Foundry number 3 is operating at a total kilowatt demand of 4,000 with a melt rate of 8.6 tons per hour, using a power utilization of 75%, they're able to achieve a pour rate of 6.5 tons per hour. In this case, the power density is 400 kilowatts per ton, which is substantially higher, as shown in the previous examples. As a result, we have now reduced the kilowatt of demand to 4,000 kilowatts, yet we are still maintaining a pour rate of 6.5 tons per hour. Next slide. Okay, Foundry number 4, which is a medium frequency batch melting system, which I noted previously is 7% more efficient than a heel melting operation. This allows a further reduction of the kilowatt or kVA of demand while still maintaining basically the same production. The higher efficiency combined with higher utilization offered by multi-output power systems results in a demand of only 3,000 kilowatts. Again, medium frequency allows us to increase the power density and reduce the size of the furnaces. This is a batch butterfly operation, whereas one furnace is being melted while the other furnace is either off or at hold for melt preparation and pouring. Once one furnace is completed its melt cycle, the melt process begins on the second furnace, resulting in a very high power supply utilization up to as high as 95%. As compared to the previous examples, we have reduced the kilowatt demand substantially while still maintaining a similar pour rate. Next slide. While Foundry number 5 is still a medium frequency batch melting operation, it is shown as a multi-output system powering 3 furnaces simultaneously. Depending on the operation, it may be difficult to achieve high power utilization using only 2 furnaces. In these cases, a 3-furnace system can be used with 1 furnace melting, the second in a melt preparation, and a third furnace would be pouring. This increases the time allowed for both pouring as well as the other melt cycle functions that we discussed earlier, including slagging, chemistry analysis, and charging. Similar to Foundry number 4, this system is 3,000 kilowatts, but has a power utilization at 100%. Therefore, can achieve 6.5 tons per hour. And also note, in this case, we've increased the power density up to 750 kilowatts per ton, which is achievable at medium frequency batch melting systems. Next slide. This chart shows the comparison of connected kilowatts for each of the example foundries. You can see that although all 5 examples are producing 6 to 7 tons per hour, Foundry 1 uses substantially higher kilowatt demand versus Foundry number 5, about 40%. This is the result of power supply utilization, efficiency, and performance. As the power supply utilization goes up, the kilowatt demand required for the same production goes down. Next slide. This slide shows how this could affect the total demand cost for a given month. For example, using $10 per kilowatt of demand, Foundry number 1 would have a demand cost of $50,000 a month per Foundry number 4 and 5, which only have a demand cost of $30,000. That's a difference of $20,000 a month, or $240,000 over a year's time. Next slide. Okay, looking at this from a cost per ton, this slide shows demand paid per ton poured. Foundry number 1 paid almost $23 per ton versus Foundry number 4, which was just a little over $14 per ton. Foundry number 5 was less than $14 per ton. As a result, you can see Foundry number 5 or even Foundry number 4 would have substantial competitive advantage over Foundry number 1 and Foundry number 2 as a result of using older technology and less efficient technology. Next slide. So to conclude, since the melt shop is the largest area of energy consumption in the foundry, it will offer the best opportunity for energy and demand cost reduction. Optimizing melt equipment utilization will minimize kilowatt and kVA demand and maximize tons poured. New induction technology offers increased performance, higher efficiency, and enhanced flexibility to achieve high power utilization and lower cost of operation. Proper maintenance and operation of the system will also reduce energy usage. And I guess at this point, I guess I'll open it up to any questions or answered questions.
Thanks, Mike. So if anyone has a question, go ahead and type it into the question box in the dashboard. It should be right below where you can see your audio information. So we'll give it a couple minutes to see if anyone's got anything they want to pose now. Again, there will be another opportunity later on at the end of the session. All right, doesn't look like we have any now. So, Jared, if you want to go ahead and get us started with Dick, and we'll address any other questions at the end of the session.
Fantastic, great. This is Jared Burke again with Power Solutions. Again, thanks, Mike, for your presentation here. So next up, we've got Dick Winsimius. Dick worked as a plant engineer with CWC Textron and as plant engineering manager for Canon Muskegon for 30 years. He's also served as a Foundry advisor to Power Solutions and is a corporate member of AFS. He's going to be speaking about reducing costs and maintaining production, his true story using Power Solutions technology.
Hello, I would like to thank you, Jared, for the introduction. You want to move to the next slide. I've got just a slight delay on my PC here, so I'm going to try to stay moving forward here. Right now I'm looking at the facility overview slide just came up. Canon Muskegon is a producer of master alloy for the investment casting and aerospace industry. We operated a facility with 6 furnaces in it. They were 4 vacuum furnaces that comprised a 2,000 kW power supply, a 1.5 megawatt or 1,500 kW, 1,000 kW, and a 600 kW. And then they had 2 air melt induction furnaces that were 20,000 pound furnaces, and they were operating at a 2.7 megawatt or 2,700 kW power setting. Next slide, please. So we recognized early on that we had several places we could save on our utility bill. The first thing we did, we investigated making sure that we had our sales tax set up properly so that we weren't paying sales tax on our energy usage for industrial processing. Next, we looked at maximizing off-peak melting. Then we looked at our maximum capacity charge, and that was a charge that once we had 115 coincidental peak time period of melting, that would set the capacity charge that we would have to pay a penalty on for the next year until we could reduce that. The next place we looked was to say when we were melting on peak, how could we manage our peak demand charge? And then the final program we got involved was with an interruptible power program where we signed up that if we received a call from the utility due to high load conditions, that we would turn our equipment down and operate at a lower set point. That was all a manual operation. Next slide. So what we faced were reducing our charges. We had an old system that was pretty ancient and was coming out of service support because the parts were no longer available to maintain it. We were looking for something that would give us better and faster real-time control. I wanted to be able to do some bill estimating so that we could help with our variable cost on a month-by-month basis, forecasting to our accounting department. I wanted to be able to look at some loads by line, one line basically where they were used. We had no all the furnaces at full power simultaneously, we would have hit that 11 megawatt load. With the power it system that we replaced our old step limiter system with, we were able to operate, and we initially started off at 5.7 megawatt set point. We were able to reduce our monthly peak penalty charge down to $62,000 per month, or we had roughly a $58,000 per month savings. After we operated for roughly a month at that set point, we drove it down even further to 4.5 megawatt, which gave us some additional savings. We dropped from a 62K penalty down to a 49K penalty. So with the new control system, it ensured us that we could meet all of our melting demands, but yet still have control of what we were paying for our peak demand for our power. Next slide. So, we had a pretty easy payback justification when we went through this. The system, had a simple payback of 10 months. We had the first year of energy savings was incrementally looked at, and it created $1.7 million worth of sales revenue based upon what we saved, because everything we saved was equivalent to dropping down to the bottom line as profit. Next slide, please. So the demand management platform that Power has is a demand control, a demand response, dynamic pricing, and then energy efficiency. The demand control portion I utilized at Cannon Muskegon for controlling my off-peak and my on-peak maximum demand set points. I utilized the demand response portion of the load control for responding to the brownout conditions automatically. And then dynamic pricing would be used in a market like California or places like that that have a floating marketplace. And then the energy efficiency is a operation where they can go in and trim VFD drives and things of that nature, and it's used primarily in refrigeration and freezer applications, which is the other side of Power-It's platform that they support. Next slide, please. This next slide is showing basically a facility and what it would look like. You can see the 3,954 kW peak demand. That could be that one 15-minute time period during your on-peak when you had a coincidental peak, and you would pay in our case at Canon, we paid $11 a kW. We would have paid $11 times 3,954 kW. The peak demand, the coincidental peak demand charge, is basically the rate at which you're consuming power, not the power you've actually consumed. So you could visualize that driving down the road at 100 miles an hour versus driving down the road at 55. You're going to get much better fuel economy. At 55, you're going to get to the same place. It's just going to average out over time. So that's what we were looking to achieve with the demand control. Next slide, please. With the automated demand control implemented, basically what we were able to do were to take those high peak loads and shift them by 15 minutes into the next debit period. Because of the physics of melting, you still need to have the same number of kilowatt hours of consumption, but there again we're utilizing and averaging that in so that it's smooth rather than a real high peak. And in Mike's slides, he went through some of the facility melting operations where there was dead time in the melt operation and you're trying to smooth in. And that's exactly the time frames that we took advantage of at Canon Muskegon by doing demand management and demand control. We were able to shift our melting time period at a reduced peak power, lasted a little bit longer, but we took significant cash advantages of being able to smooth that trend line to a set point. Next slide, please. The automated demand response that we signed up for originally required us to manually go out and adjust and set down the set points. With the Power It system, we were able to dial in to the system, and I would always receive the notice for the brownout conditions, and I would have to call the plant and get the furnace operators to turn down their power. With the automated demand response, we were able to install a phone switch so that once I received notification from the utility that we had to go into an event, I could dial in and automatically set the automatic system from our 4,500 kW on peak demand set point. We could automatically set it down to, in our case, we set back to 2,500. We reduced 2,000 kW. And for that, I received a $4 per kW credit each month on my utility bill, so I had an additional $8,000 savings. Had we not set back to the set point we had agreed upon, we would have paid a penalty of $50 per kW. Next slide, please. So basically, this slide is somewhat of a comparison for what we achieved at Canon Muskegon Corporation. Initially, there was no control on the system, upper portion of the slide. You can see our set points were all over the place. We installed a step limiting control, and a lot of facilities out there have an old PLC where they look at a set point and they get some step control in there and they're able to control their power. But yet you still have lots of peaks and lots of areas where you can shave, but due to the interference that the step control contributes to the operation, you have to have an artificially high set point. When we installed the automation and the automatic system that integrated seamlessly into the inductotherm equipment that we were using, we were able to lower our set point because now the system would reduce the minimal amount that was needed to maintain our set line. Next slide, please. And that was how we achieved the savings that we talked about earlier in my presentation. So the slide we're coming into right now, these are some actual case studies. Each one of these colors on this graph represent 1 day of a 30-day month period of time. And you can see by looking at these colors, there's only a few occurrences that the system was spiking up above, you know, the 800 kW set point. This was a small facility in Wisconsin. They were able to go in and save 200 kW at roughly $20 a kW. So they had a pretty significant savings by putting in an automated system. Next slide, please. That small foundry, they were operating 4 different power supplies that were down in the 200 to 250 kW range. This facility is a medium-sized facility. There again, you can see they had an on-peak, off-peak time period. Their on-peak started roughly at 10 o'clock in the morning and it went to 1800 in the afternoon. You can see the number of occurrences where they were spiking up above a set point that they wanted to operate at. Once the automated system was in, it kept them down and kept it depressed during that on-peak time period to give them some significant savings. Next slide, please. So I think from here out, I'm going to pass this back over to Jared. He's going to cover some case studies of some actual installations and savings that PowerIt has been able to achieve, and I will be available for questions at the end of his presentation. Thank you.
Great. Thank you very much, Dick. This is Jared Burke with PowerIt. I wanted to share a success story here. One of our customers, Donsko Incorporated, they've standardized on our energy management system, Sparrow Demand Manager, across multiple melt shops. Utilizing our technology, they've been able to reduce their peak demand charges by 10%, which has equated to just around $65,000 a year in annual demand control savings. Similar to Dick's experience at Canada Muskegon, you know, they haven't suffered any production losses or deviations as a result of managing their peak demand. Similar to Dick's experience, they've also been able to participate in some demand response programs, or these interruptible load programs. One of those is very similar to what Dick experienced at Canada Muskegon, where they get a 24-hour notice, and then they shed load, and they're able to save around $30,000 a year by participating. One of the other programs that they've been able to take advantage of is called the Synchronized Reserves Program, or a fast demand response. This is where they only have 10 minutes of notification in which they have to shed load. Something that they really would never have been able to participate in had they not automated their demand response. So using the Sparrow Demand Manager platform to automate this fast demand response program, they've been able to receive an additional $66,000 in annual cash back from their utilities or demand response provider. Some of the other success stories that you can see that where Sparrow is being utilized, you can find them on the PowerIt Solutions website. We've got Blackhawk, Mexico success stories, Eagle Alloy, again, Canada Muskegon, Hitchner Manufacturing, Rochester Metals, and Pacific Alloy Castings. And finally, you know, we've talked a lot about, or Dick has talked a lot about the experience he's had utilizing Sparrow Demand Manager to reduce his peak demand charges, to utilize, to participate in demand response. Some of the other benefits of our technology, again, the Sparrow system provides real-time visibility to the plant-wide energy consumption. This can be used for maintenance and seeing if something's going wrong with a furnace or a power supply. Also for safety, to make sure that pieces of equipment are consuming the correct amount of electricity. The Sparrow system is a fully productized solution, and as such, there's software updates that go out, and for when things changes within your facility, when you add a piece of equipment or remove a piece of equipment from your facility. You can very easily change the software and update and add those equipments into the load mix. The system's also fully used by the end user. So when Dick had our SPAR system in his facility, he was fully in control of all the rules and regulations and set points, and manipulated and utilized the system himself. He didn't require Powered Solutions to come in and change anything or to really manage his system. It was his tools to work with. So with that, I want to thank Mike Nutt again from Inductotherm and Dick. Hopefully you can help us facilitate that.
Yep, we'll give it a few minutes here for people to go ahead and type their questions in. I see a couple of you have your hands raised. If you could go ahead and type your question in the question or chat box. It should be right under where you clicked to raise your hand. Anyone have anything to ask? If not, I think we can go ahead and end the session. Thank you all for attending the webinar. And if you have anything, unless you have anything else to add, Jared, I think we can go ahead and say goodbye.
Nope, that's it for us. Again, I want to thank everybody for participating today. And if you've got other questions, our contact information is up there, both my own and Mike's as well. And when we send the presentation out, we'll also have Dick's up there at the end as well.
One other thing, Jared.
Thank you, everyone.
One other thing, Jared.
Go
This
ahead.
is Dick. If they do have any questions, please feel free to stop by and see us at the AFS booth. I will be there with Power It, and I believe Mike will be there at the Inductotherm booth. So.
Yeah, that's correct. I will be there as well.
Great. Yeah, that's a good point. Yeah, Powered Solutions will be in attendance, so absolutely feel free to come stop by.
Okay. Thank you very much, everyone.
Thank you.